Hi all, welcome back to the discussion on quantum optics. Today we are going to discuss the quadrature operators for a single mode field. So we have seen that the electric field operator can be represented as Ex E0. In general, we can write it is A of t is called annihilation operator and A dagger of t. And I have explicitly given the time dependence of A of t and A dagger of t just by using the Heisenberg picture. So according to the Heisenberg picture, the equation of motion is IH cross dA by dt. So if you consider any operator A, the time evolution of this operator can be found by using this differential equation. So H cross dA by dt equal to the commutator AH. Okay, so I have shown here how to find the explicit time dependence of A. In quantum optics, the Hamiltonian, we can write A dagger A plus half H cross omega. Is A dagger is called creation operator and A is called the annihilation operator. Okay, so then IH cross dA by dt, I can write which is equal to the commutator AH, and we know the Hamiltonian, I can write A dagger A plus half H cross omega. Okay, so this half, if you want, you can introduce an identity operator as well here, half identity operator. Now this A commutes with identity operator, so there is no need to take that commutator, but we have to find the commutator between A and A dagger A. So the H cross omega we can take commonly outside. Okay, so H cross omega A dagger A, and using the commutation rule, this can be split into two commutators. Suppose you have the commutator A B C, this can be split into two. The commutator between A and B with the C outside, the C has to be written on the right side, plus the commutator between A and C. Here the B has taken to the left side, so B is on the left side and C is on the right side. So accordingly we can split this into two commutators. A dagger A can be found by one commutator between A and A dagger, other one is between A and A. But the commutator between A and A would be 0 because A commutes with A, so there is no need to write that commutator explicitly. And we can write the first commutator, the commutator between A and A dagger, and here we have to take this A to the right side. Okay, so I have taken the A to the right side, so A dagger. Now A dagger is just simply an identity operator or 1. Okay, so therefore this become H cross omega. So the left side is IH cross dA by dt. Now we just rearrange it and integrate it, and I can show that this A would become e raised to minus I omega t A of 0, or this A of 0 simply I have denoted as A. So this become A of t is A e raised to minus I omega t. And similarly we can write A dagger, where A dagger of t would be A dagger e raised to plus I omega t. So that is why I have written my electric field operators in terms of this A and A dagger by introducing the explicit time dependence for the annihilation and creation operators. Okay, so now this is a time to introduce the quadrature operators. So the two quadrature operators I am going to introduce by symbol x1 and x2. So simply x1 is half A plus A dagger and x2 is 1 by 2i A minus A dagger. Okay, so we can see what is the relevance of this x1 and x2 later. So first of all, what I have to do is I have to represent the electric field operators in terms of this quadrature operators. So for that we can find A and A dagger in terms of x1 and x2. Okay, so I can show that this A, the annihilation operator, is simply x1 plus ix2. You can do it yourself, and A dagger, therefore A dagger will be simply x1 minus ix2. Okay, so here we have these two equations. Okay, let this be equation number 1, and this can be equation number 2 and equation number 3. Okay, so by using equation number 2 and 3 I can find expression for A and A dagger that I represent as 4 and 5. Now just substitute this 4 and 5 into 1. Okay, so if you just substitute 4 and 5 in 1, I can represent my Ex as epsilon 0 x1 plus ix2 e raised to minus I omega t and x1 minus I x2 e raised to plus I omega t, and the spatial dependence is sine of kz. Okay, so just rearrange everything. Okay, we have 2x1, and here we have a e raised to minus I omega t raised to plus I omega t. So if you take x1 common, this become e raised to I omega t plus e raised to minus I omega t. This become ix2 e raised to minus I omega t minus e raised to plus I omega t. Okay, this algebra you can do it yourself. Just go through it. Okay, just pause it and do it yourself, and you can show that this electric field operator you can write as 2 epsilon 0 x1 cos omega t plus x2 sin omega t times sine of kz. Okay, so this is similar to you can see that this x1 and x2, one is cos is coming, other one is sine is coming, so the phase difference between the cos and sine is pi by 2. So therefore I can say that the x1 and x2 are the electric field amplitude oscillating with phase difference of pi by 2. And we can see this kind of operators in harmonic oscillators as well. So it is analogous to the position momentum operators of harmonic oscillator. Okay. So remember, there is no exact meaning for the position momentum operators in quantum optics for the field. Okay, but the x1 and x2 have a similar structure, the similar mathematical structure of the position operator and momentum operator that we have already dealt in the harmonic oscillator problem. Okay, now the commutator x1 and x2, I can show that by using these simple commutation rules. Just substitute the expression for x1 and x2, and we can show that this the commutator x1 and x2, it simply become I by 2. Okay, so all these steps I have shown here. I have in detail I have shown all the steps. Just pause it and do it yourself, and convince that indeed the answer, the commutator x1 and x2, would be I by 2. Okay, now we can put the equation numbers. So this can be equation number 6, and the commutator relation can be equation number 7. So this is a commutator between x1 and x2. So once you know the commutator, we can easily find the product of uncertainty of these operators. So from the general uncertainty principle, delta I delta B will be always greater than or equal to 1 by 2i, the expectation value of commutator AB. Okay, so that can be represented as equation number 8. It's equation number 7. Okay, so just substitute delta x1 as x1 and x2 in terms of a and b. So it become delta x1 delta x2 must be greater than or equal to 1 by 2i, and the commutator x1 x2 is simply I by 2 times the identity operator. Okay, this one I will cancel, and 1 by 2 will become 1 by 4. The expectation value of identity would be 1 in for any state. So therefore the delta x1, the product delta x1 delta x2, the product of uncertainty of quadrature operators, should be always greater than or equal to 1 by 4. Okay, so the product of uncertainty in quadrature operators quadrature operators in any state. So whether we have different possible states in quantum optics. Okay, so we have discussed only one possible state right now, that is called the Fock state or number state. There are many other states called coherent states, Q state, etc. So if you take any possible states, the product of uncertainties of x1 and x2 must be always greater than or equal to 1 by 4. Okay, so further now we can calculate the product of delta x1 and delta x2 for the number state, because we are already familiar with the number state. Okay, so for the number state, what is the number state? Number state is the eigenstate of the number operator. A dagger A acting on n must give n ket n. So this ket n is called the Fock state or number state. Okay, now for this number state, I can calculate what is delta x1 and what is delta x2. I have to calculate delta x1 and delta x2. So remember, delta x1 is the uncertainty in x1 is the square root of the expectation value of the square of operators minus the square of the expectation value of the operator. So this is a definition for the uncertainty. Okay, So in order to find delta x1, I have to calculate the expectation value of x1 operator and the expectation value of x1 square operator. So first we can calculate what is the expectation value of x1 operator. So n x1 n in number state, where x1 is a plus a dagger by 2. Now this expectation can be split into two, n a n and n a dagger n. N a n will give the a acting on ket n would give root n into n minus 1, and a dagger acting on ket n give root n plus 1 times n plus 1. So we will get two expectation. Okay, now two inner products, so both the inner product will become 0 because this root n is just a number, you can take it outside, and you have to take the inner product between n and n minus 1. The n and n minus 1 are the different eigenvectors corresponding to the different eigenvalues, so that must be orthogonal to each other. Since a dagger a is a Hermitian operator, the eigenvector corresponding to the different eigenvalues are orthogonal. So therefore the n and n minus 1 are orthogonal, and hence this inner product would become 0, and this inner product would also become 0. Okay, so if you want, I can add one more step here. So what I can do is, so this can be further step, I can write this equal to root n can be taken outside, this would become n minus 1, and here root n plus 1 is just a number taken outside, n plus 1. Okay, not root 2, this would be root n. Okay, now this is n, the ket n minus 1 and bra n are orthogonal, so this inner product must be 0, and this inner product must also be 0, and hence the expectation value of x1 must be 0. Similarly, I can easily show that the expectation value of x2 is also 0 for number state. Okay, now we can find x1 square, the expectation value of x1 square. The expectation value of x1 square is n x1 square n. So what is x1, which is a plus a dagger square by 2. Now when you are taking the square of a plus a dagger, we should be very careful, because this a and a dagger are operators, so in general they will not commute each other. So if you expand a plus a dagger the whole square, you will get 4 terms. One is a square, other one is a dagger square, and you will have a dagger and a dagger. So you will get 4 terms. Now obviously, what would be the expectation value of n a square n? So a square acting on n will give root n into n minus 1 into n minus 2. So okay, so the action of a square acting on n decreases the quantum number by 2, so n will become n minus 2. So this is simply a number, so I can take this number outside, root n minus 1, and we'll have an inner product between n and n minus 2, and this inner product would be obviously 0, because they are the eigenvectors corresponding to different eigenvalues, so that will become 0. Okay, so the n a square n, so this expectation I can split into 4. One is n a square n, and other one is n a dagger square n. Then you'll have n a dagger a plus a dagger n. So first two, the expectation would straight away it becomes 0. Now the last expectation, that would be non-zero. Now that we can find. Okay, now in order to find it, what I can do is I can change a dagger in terms of a dagger a. Okay, because we know that a dagger a acting on n is n acting on n, so n times ket n. Okay, because ket n is the expectation value of the number operator, but we don't know what is the action of a dagger acting on n. So what is the result of this? So in order to find this, you can use this commutation rule, because commutator a dagger is 1 or identity. So therefore that is a dagger minus a dagger a is identity, or a dagger is identity plus a dagger a. Okay, so this a dagger I can write identity plus a dagger a. Okay, so this become 2 a dagger a plus identity. So there will be two inner product. One is n 2 a dagger a acting on n, so that become n 2 n n, and the other one would be simply the inner product n n. So this would become 2n times inner product n, and this is simply n, that would be 1. So this is also 1. So finally, this become 1 by 4 to n plus 1. So what is the left side? The left side is the expectation value of x1 square in number state, for the number state get n. Okay, and similarly I can find the expectation value of x2 square in the number state. It is 1 by 4 to n plus 1. Okay, so both x1 square and x2 square are equal. So therefore in Fox state I can calculate the uncertainty in x1 and x2. It is by definition it is square root of x1 square, expectation value of x1 square minus the square of expectation value, and that would be equal to 1 by 2 root of 2n plus 1, and the expectation the uncertainty in x2 would be 1 by 2 root of 2n plus 1. So finally the product of the uncertainties delta x1 delta x2 would become 1 by 4 2n plus 1. Okay, now we already know that the product of uncertainty delta x1 delta x2 must be always greater than or equal to 1 by 4, and that is true here. Okay, so this right side is always greater than 1 by 4, so this is valid. Okay, so this equation, this the result that we have got, it is already validating our uncertainty principle. Okay, now what about the minimum value of this product of uncertainty? If you calculate the minimum value of the product of uncertainty, that is possible for n equal to 0. That is for vacuum, in vacuum when n equal to 0, the product of uncertainty would be 1 by 4. So that is the minimum uncertainty possible for the quadrature operator, the minimum uncertainty of product of the quadrature operators. So that is the vacuum state minimizes the uncertainty product of quadrature operators.